81. A balloon filled with helium gas takes 6 hours to deflate to 50% of its original volume. How long will it take for an identical balloon filled with the same volume of hydrogen gas instead of helium to decrease its volume by 50%? Okie dokie. So welcome to the effusion and diffusion part of the gas chapter. This part is basically talking about the rates and how fast one gas will flow around its container. Now in this case, they tell us that we have two different gases. We have helium gas and we have hydrogen gas. So helium, it's a noble gas. It's in group 18. And helium exists by itself. It's not one of the diatomics. So helium basically takes 6 hours to deflate to 50% of its original volume. Now they're asking for how long, so what time will it take for hydrogen gas to basically decrease by the same percentage, 50%. Now remember, hydrogen gas, hydrogen is one of your diatomics. So when I talk about hydrogen, I'm not just going to write H, but I have to write H2. And in this case, we're solving for how long it's going to take hydrogen to come down to 50% of the original volume. Now, the effusion, the rate of effusion formula that we're going to use here is this one. Now, it may look a little scary, but I promise you it's not. But there's a key thing here. Generally, we talk about rates in terms of one substance over another. Now, does it really matter which one we label as A and which one we label as B? Absolutely not. I guess since helium is on the top, I'll say that this would be representative as A, and then hydrogen, since it's on the bottom, we're going to represent that as B. So we could basically say that it's going to be the rate of helium divided by the rate of hydrogen, and that equals to the square root of mm, and mm is molar masses. But now, they didn't tell us a rate. They only told us a time, right? 6 hours is the amount of time. But remember that a rate, and we're going to see this in later chapters when we talk about kinetics, but a rate is basically the amount that something is either increasing or decreasing divided by time. So in this case, sorry about that, guys. So in this case, if the amount that is being dropped down, it's deflating to 50% of the volume. If the amount of helium that's being deflated is the same as the amount of hydrogen, we could basically cancel this out, right? Because if they're the same, we don't care about that variable. And now we're just left with the time, and that's where the 6 hours come in. So in this case, what I'm going to do, and sorry about that, I'm going to just rewrite this a little bit. And I'm going to say that instead of saying rate A, I'm going to basically say that it's the amount, and maybe I'll do that in black, it's the amount of A divided by the time. And then the same thing here. So I'm not going to say rate. I'm going to say it's the amount divided by the time. But remember, if the amount is the same for both of them, I can get rid of it. And if I get rid of this variable, I'll just put a 1 on the top here, right? 1 over time divided by, get rid of this, 1 over time. And now this A value is just designated to the bottom, the time of A, divided by the B value is just on the bottom here. But now, think back to algebra. What happens when we have a fraction divided by another fraction? That's keep, change, change. So if we have 1 over time, and that's of A, divided by 1 over time B, remember, keep, change, instead of division, it's now going to be multiplication, and then change. I have to flip this fraction. So it would be time B divided by 1. And if I just simplify this, remember when we multiply fractions, we multiply the numerator and the denominator. So this would just be basically time divided by time. But now B is on the top, and A is now on the bottom. You see how when we started, A was on the top and B is on the bottom, but not when you're talking about just time. When you're talking about just time and your amounts are the same, the B's both are on the top and the A's are both on the bottom. So I'm now just going to erase this and now come to our formula. And our formula now is time B divided by time of A. And now, here we go. We said that A was 6 hours, so I know this number. This is 6, and that's what we're solving for. We're solving for the time it takes for H2, so this would be X, right? And now the molar masses, remember, is going to be found on the periodic table. So maybe if I just bring this over here, and now I'm just going to do the math. It's going to be this equals this, X, and maybe I'll put these in colors. So X divided by 6 equals both square roots, right? And now B's on the top. B was H2, so I have to take that into consideration. So 1.008 times 2. 0.008 times 2. 2.016. And let's see, 2.016. And then for H, helium, we have 4.003. Now I can get this as to one number. So square root of 2.016 divided by the square root of 4.003. Okie dokie. And now since I did the coloring white, we don't really have to worry about the colors anymore. So I'm just going to say that this is X divided by 6 equals this long decimal value, 0.7096635. And now it looks like cross multiplication to me. So I'm going to solve for X, which was the time it takes hydrogen to deflate by 50%. And all I got to do is just times that value by 6. So sig figs, I mean, technically it should be 1 sig fig because we had 1 sig fig in the 6 hours, but I'm just going to say, 4.3 maybe? It's 4.257, so 4.3. And that's hours because the other time was in hours. And that is your final answer. And maybe I'll do this in blue. So it takes hydrogen 4.3 hours when it takes helium 6 hours to deflate to the same volume. Thank you so much for tuning in. I really hope this helps. Let me know in the comments. Subscribe to the channel. And if you want to help us out, tell your friends, tell your classmates. We wouldn't mind. Thank you so much, and I will see you in later lessons. Bye-bye.